Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to introduce linear maps and linear operators. Now, in this first topic, we're simply going to introduce the idea of a map and an operator on vector spaces. We're going to give some background, and then we will define the image and range of maps. We will give some examples as well. Now, in engineering, any signal, be it continuous time or discrete time, may be represented as a vector. So this could include voltages, sound intensities, temperatures, concentrations of chemicals, or global positioning system coordinates. The purpose of engineers is to extract information from such signals and make use of it appropriately. So we're going to start with an input vector. That input vector will then be placed through a mapping A, and that will produce an output vector V that hopefully has more information or more useful information than the original input vector. For example, we may be calculating the average value of a signal or a vector. We may be trying to reduce the noise within a signal, or we may be trying to increase the resolution. For example, we may be trying to display an analog television signal on a 4K screen. In each of these cases, the output is another vector. Now, in the first case, the output is a single value, but you can think of it as being R1. In the second, the output vector has the same dimension as the input vector, however, hopefully with less noise or static. Finally, in the third, the output is going to be a higher dimensional vector than the input. Now, given two vector spaces U and V, and from here on in, we will represent vector spaces with this script U and script V. We will say a map A is a function that takes a vector in one vector space and maps it to a vector in another vector space. In this case, the original vector comes from U and is mapped to V. So we will represent this as follows. Vectors in U are input to the mapping A, and the output is a vector in the vector space V. We will also write this as in the notation A colon the vector space U being mapped to the vector space V. Now, for A to be a map, A must map every vector in U to some vector in V, just like a function of the real numbers. For a function to be truly a function of the reals to the reals, it must take every single real number and map it to another real number. So under this definition, sine is a function. However, the tangent function is only a function on the real numbers excluding multiples of pi plus pi over 2. Now, what we will say is if U is a vector in the vector space U, then U will be mapped onto the vector A times U, which is a vector now in the vector space V. Now, once in a while we may actually write the argument of the mapping A in parentheses, especially if we're going to avoid confusion. For example, we may consider what is the image of a linear combination of two vectors in U. In this case, we would wrap parentheses around that vector to demonstrate that the A is being mapped onto all of, or the result of, that linear combination. Now, given a mapping A, mapping the vector space U onto the vector space V, we will refer to U as the domain of the mapping A, and we will refer to the vector space V as the codomain of the mapping A. Now, if A is a map that takes vectors in U and maps them to other vectors in U, that is, the codomain and domain are the same, we will say that A is an operator. Now, if U is a vector in U, then A times U is a vector in V, and we will say that A times U is the image of U under the map A. Now, if V is a vector in the codomain, and there is a vector in the domain U such that V is the image of U, then we will say that U is a pre-image of V under the map A. However, not every vector in the codomain may have a pre-image. Now, if S is a subset of the vector space U, then A applied to S is going to be the collection of all images A times U for each U in the subset S. So basically, we will say that A times S is the image of S under the map A. Now, if we now consider A times the entire vector space U, this will be the collection of all images A times U for every U in the domain U. We will also refer to this as the range of the map A. So the range of a map is a subset of the codomain. In some cases, the range may be the entire codomain, but in other cases, the range may be a subset of the codomain. Now, here are two examples of operators, each mapping R3 to R3. The first one is actually mapping rectangular coordinates to cylindrical coordinates. The second is mapping rectangular coordinates to spherical coordinates. Now, you will be using these mappings in your second year courses in calculus. Here are three other mappings. The first is a general map. The second and third are operators. The first maps the vector xyz onto the average value. So this maps R3 onto R1. The second subtracts from the vector xyz the average value of those three entries. The third, on the other hand, averages each point in the vector with its neighbor or neighbors. So, following this topic, you now understand the idea of a map or a vector between vector spaces. A map takes vectors in the domain and maps them to vectors in the codomain. An operator is, of course, when the codomain equals the domain. You also know the terms image and range. So we can take the image of a vector, the image of a subset of the domain, or the image of the entire domain. And another term to describe the image of the entire domain is the range of the map. We also looked at some basic examples. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!